referring back to our geodetic data, if we look at the various ellipsoids that give the polar radius, and then we take each of those polar radii going from all of these ellipsoids down, the Clark ellipsoid has been the one of 1880, has been the one used in the United States for all non-military and non-NASA related measurements. We still use on a day-to-day basis. If you take a topographic map, you know, and you're going out like a 7.5 quadrangle, and you're going out navigating with a topographic map put out by the U.S. Geological Survey, they're using the Clark ellipsoid right there. But you'll notice that when we take these various polar radii lengths in feet and divide them by 43,200, you can see the numbers we get right here. Remember, the height of the pyramid is estimated at 482.7575. So looking at this, what you'd see on here, which one would be the closest? Well, you notice it's come out very, very close to the satellite surveys. Given that it's very and see, when you got to ask yourself, well, why is there a difference between this, the satellite survey of 72, and the satellite survey of 80? Well, if we did another one again with as high a degree of accuracy, we would discover there's still going to be a discrepancy. And the reason is that the Earth spinning through space, there are various tidal forces working on the Earth which are constantly causing it to distort its shape by up to 2 or 3 or 4 or 500 feet. So we never would be able to get more accurate than 300 or 400 feet because the Earth itself is changing shape. And if we were to measure it every year for the next 10 years, we would get 10 different numbers. They'd all be very close, but they would deviate somewhat because the Earth itself, there are tidal bulges. You know, where's the moon relative to the Earth? That's going to affect. If the moon and the sun are on the same side of the Earth, that will affect the shape of the Earth up to being several hundred feet measured over the diameter of the Earth. And so it is not amiss to say that the pyramid enshrines a measure of the Earth that could be considered as accurate as those determined by modern satellite surveys. That to me is a very profound insight, because it does suggest that somebody once upon a time was able to measure the Earth size and shape with that level of precision. And if they were able to do that, what's the implication of that? See, that's the interesting part. Because no primitive culture, using the method of Eratosthenes in about 300 BC in Greece, he measured the Earth and was generally considered to be quite accurate because he was able to get the circumference of the Earth within about 500 miles of its actual measured circumference by using the methods available to the ancient Greeks, you see. And he was considered to be the first to measure by basically putting a stick in the ground and measuring the angle of the shadow on the longest day of the year over a couple of successive years. That's actually an exercise we do in the sacred geometry class because it's very interesting how he did that. But he was considered to be, you know, pretty proficient because he was able to determine that the size of the Earth was, the circumference of the Earth was, you know, 25,000 miles, when it's generally considered to be about 24,800, depending on where you measure it. So he was, you know, maybe within 50 miles of the actual dimension of the Earth, but nowhere near as close as the pyramid would have been. So again, even if the pyramid was built 4,200 years ago, you know, you got to say who 4,200 years ago had the technology to measure the Earth with that degree of accuracy. Now, that we know of, nobody 4,200 years ago did, or how they would have done it, we don't know. But on the other hand, if it turns out that the pyramid could be much older, it leads us back to the, you know, going back 10,000 or 20,000 years. This to me is one of those little, sort of like the little crack in the dike, that if you don't keep it plugged, the whole edifice of contemporary knowledge could get swept away. Because we can't acknowledge that somebody 10,000 or 20,000 years ago was scientifically sophisticated. That was the days of Cro-Magnon man and Alley-oop living in the cave and so forth. Cavemen, which is a silly idea actually. Yes, I'm sure people did take refuge in caves when things got really crazy out here. Yes, I think people did take refuge in caves. But see, this is one of those things, again, that if you accept that it's not just a coincidence, it opens up a whole can of worms that mainstream science generally doesn't want to address. Because we're the epitome of scientific evolution right here and now, right? Nobody, before we built satellites, could have measured the Earth to within a couple of 100 feet of its actual dimensions. So, given 2 seconds of time, 1/43,200th part of the daily rotation, a point on the equator will travel a distance precisely equal to the perimeter of the Great Pyramid's base as measured with the socle. In 1/2 second of time, a point on the equator will rotate a distance equal to one side of the base of the Great Pyramid measured with the socle. So here you have a time and space measure integrated into one. The time measure comes in because it's the span of time that the Earth has moved. In 2 seconds, the Earth has turned and moved a distance within a fraction of an inch, being the distance around the base of the Great Pyramid. And so the height of the Great Pyramid measured with the socle is 1/43,200th part of the Earth's polar radius. So therefore, the Great Pyramid is a model of one hemisphere of the Earth at a scale of 1 to 43,200. So if we took the Great Pyramid and we created a duplicate and turned it upside down and put the two together base to base, that would now give us the polar diameter. And there's something else that's beyond the scope of today's talk, which we get into in an actual sacred geometry class. And this is looking how the pyramid is also the solution of the squaring of the circle, the ancient geometry problem of the classical world, the squaring of the circle. And that has very important implications for understanding the Great Pyramid as a three-dimensional map of the Earth. Because the Great Pyramid's square base is to its height exactly in the same relation as the radius of a circle is to the circumference of a circle. So you could picture that what's happening there, that means that in all maps you have a line of constant proportion, a line of where the scale, you know that all maps that you look at, there will be somewhere on the map where you have an accurate scaling, and as you move away from that line of accurate scaling, the maps become distorted. Well, if you've got a square and a circle of equal perimeter, you see, the Earth's equator, think of as the circle, and you think of this pyramid being enlarged 43,200 times, its square base is now the same distance around as the Earth's equator, right? So if you're mapping from the arc, the circular arc that's the Earth's equator, taking that and flattening it out, and now mapping it onto the base of the pyramid, the 43,200 times bigger pyramid, it's going to be exactly the same length. So there's going to be no distortion around the perimeter of the pyramid's base and the height of the pyramid, which is exactly the polar radius of the Earth. So that, from the standpoint of cartographic information, the particular geometry of the pyramid is very relevant because it is the solution to the squaring of the circle problem, which is something we study extensively in a sacred geometry curriculum.